So in this talk, we're going to recommend the use of two new class templates. We have indirect value and polymorphic value, and our intention is that these classes will make the design of composite classes much, much simpler than it currently is, and much more likely to be correct. But first of all, we'll look at some motivation. We're going to dig into some of the challenges of composite class design and see which problems remain unsolved by the current repertoire of standard library vocabulary types. And then, if time permits, we'll dig into our implementations of these two new proposed types. So, as I would assume most people are probably familiar with in this room, C++ and C and Python and other things define these sort of record types, which let you group together data that's logically associated. And C++, along with some other languages, let you, add to that associated data some methods which act on that data. And that would allow you to do things to the data while preserving some invariance. So it gives you a way to interact with the data without combining things in invalid ways. So here we've got a circle with its position stored as a couple of doubles, and its radius, and then color kept as a string. Many of the examples in this are not very sensible. Please don't store color as a string. It's going to cause you trouble. So yeah, C++ being a sort of open-minded language will allow us to use our own types inside classes to define member data. So if we'll hark back and see we've got a pair as position. So position.first, position.second, not my favorite API. So why not have point with X and Y defined inside it? So that's good, and that's a composite class. So that's a class made of other classes. So for these composite classes, we'll have a desire to move the objects around, possibly construct them, probably destroy them, quite likely, and maybe copy them. So the language defines these special member functions which are used to create these copies, moves, or destructions of instances of our class. So our circle, you might want to give it its color and radius and position on construction. And then you have a function to copy it, which takes this const circle ref, a copy to assign it to a const circle ref, and then two functions to move it, and a function to destroy it. So hopefully all this is reasonably familiar. Under certain conditions, the compiler will generate these special member functions for us, and then members of the class will be in turn copied, moved, or deleted as is appropriate. And we can use the enduringly awesome compiler explorer to see an example of this in action. So this is just enough code to provoke the compiler into showing us what we want to see. So we have a class with a declared but not defined constructor, copy constructor, and destructor, and another class which contains an instance of that class. And then we've got some function which takes in an instance of the composite class, creates a copy of it, does something with the copy. We don't know what any of these things do, and we'll have a look at the compilation output. So this was compiled with no exceptions turned on to get rid of all the unwinding noise, with optimizations turned up nice and high. And you can see in our do something code, it's calling the copy constructor of A, and it's calling the destructor of A. And that's because the compiler has generated a copy constructor for B, which needs to copy and destroy the components inside. So hopefully no surprises to anyone there. So we can specify these special member functions ourselves. The compiler will sometimes generate special member functions for us. The rules around when it does and doesn't are unfortunately a little bit complicated. I'm not going to spend any time talking about that. And the generated special member functions will, as I said, be these member-by-member calls to the appropriate special member functions of each of the member objects. So that sounds good. And the reason this is good is because the best code in the world is no code. And if we can avoid writing code, we won't have to debug it. So if we can get the compiler to do the heavy lifting and generate these special member functions for us, we're going to be on the happy path. So C++ and C and other things have pointers. So when a class contains pointer members, the compiler-generated special member functions will copy or move or delete the pointer but not the pointee. So we'll have a struct here with a single pointer member, a pointer to a B object, and we'll create a copy of that struct. And then the compiler will happily go away and synthesize the copy constructor for us. And now, so I don't know what the semantics of this class are, what this A having the B star inside it means, so maybe this is doing the right thing. Maybe the compiler generated copy constructor is in fact doing the correct thing, because these classes are just meant to be pointing back to some object, so maybe they're sort of, shepherds pointing at a star or something, in which case creating a new shepherd is fine, because you don't want to clone the star every time. But maybe that's not what you meant, and having these two objects pointing to the same B might be problematic. And that might require us to go writing our own versions of special member functions. And, as much as I love C++, I'd like to avoid writing code. Another design concern. So member functions in C++ can be const qualified. So you have this little keyword const stuck on the end. When an object's accessed through what we call a const access path, then only const qualified member functions can be called. And that can be quite useful for sort of forcing invariance and making things immutable. C++ being what it is, of course, you can undermine that by peppering your code with const casts immutable, but probably don't do that. So if we have a const A created over here and try and call the bar method on it, then you'll see bar was not const qualified, and the compiler will tell you passing const A as this argument discards qualifiers, so you're not allowed to do that. So no code is great. If you can avoid writing code altogether, that's good. If you can't avoid writing the code, if you can get the compiler to make sure your code is doing the right thing, that's probably the next best thing. We'll get a const access path by directly accessing a const qualified object, as we just saw, or by accessing an object through a reference or pointer to a const qualified object. That's a bit of a mouthful. Pointers can be const qualified and unfortunately can also point to const qualified objects, which leads to this rather confusing soup of consts and pointers. So at the top, no consts in there, so that one's easy. That's a non-const pointer to a non-const A. The one below is a const pointer to a non-const A, and then we have a non-const pointer to a const A, and then finally a const pointer to a const A. Since references can't be made to refer to different objects, they can only refer to const qualified or non-const qualified objects. So as we saw before, an object's member data will become const qualified when the object is accessed through a const access path. So this piece of code here, we have an A, which has got a non-const foo method inside it, and we have a B, which contains an A, and a bar method, which is const qualified, and it will try and call the non-const qualified foo inside that const qualified method, and that's going to fail with the same sort of error message before, that we've discarded qualifiers. So that's good. The compiler stopped us doing something we were trying not to do. So const propagation and reference types is the other concerning issue. So a pointer or reference member data will become const qualified when accessed through a const access path, but this constness won't propagate through to the pointees. So pointers, when accessed through a const access path, can't be made to point to different objects, but the objects they point to can be accessed in a non-const manner. I thought C++ was fundamentally broken when I discovered this. It's not. It does what it's meant to do. It works fine. But we need to bear this in mind when we're designing composite classes for const correctness. So really what we don't want to be doing is writing any code we can get the compiler to generate, or writing code that the compiler's not going to check for us. And that's the motivation for introducing these new types. So when we're designing our composite class, what options are there for components? Well, class instance members, this slide's in there because it's nearly always the right answer. If you want a car to contain an engine, then you don't need to use vectors or optionals or anything complicated. If you can just stick one of the objects inside your object, that's probably the right way to go, because the compiler will generate special member functions correctly and const propagation will all work. So that's good. So do that. If you want multiple instances of your component in your class, so we might have a talk with a speaker and an audience. So we'll have a single speaker, and then hopefully multiple people in the audience. So the standard library offers us collections like vector and map, and they support a variable number of objects. Things like vector and map have special member functions that work properly. They'll copy the things inside them, and destructors and the like will tidy them up when they're destroyed. And they also do const propagation. So vector is a value type. If you have a vector member and try and access it through a const access path, you won't be able to get hold of anything in the vector in a non-const manner or make any changes to the vector itself. So now we start complicating things, because that's where life ends up. Indirect storage. So we might have member data that's too big to be sensibly stored inside the class. If, for instance, member data is accessed really infrequently, we don't want to have it as part of our class body, because it's just going to keep, you're just going to invalidate cache a whole load. So if you can keep the big bit of your object that you don't look at very frequently somewhere else, then storing it directly as a member is not really a very appealing option, because it's going to bloat your object into something really quite large. So yeah, we might want to revisit this. Another concern is the need for incomplete types. So if the definition of a member is not available when a class is defined, then we'll need to store that member as an incomplete type somehow. So this can come about in node-like structures. So a singly linked list, probably not a very good instance of a singly linked list. We have node, which contains data, and then it's got a pointer to next. Probably should have been last or previous. Anyway, it won't compile, so we have bigger problems, because you can't stick a node inside a node before you've defined what a node would look like. I mean, even if you could, the thing would be infinitely big. So this is clearly not a tenable option. We need another way of spelling this. So yeah, we need incomplete type support here. So direct data storage, no good. Sticking things inside vectors or maps, also no good. And then in my past, there was a common pattern people would use as pointer to implementation. So pointer to implementation was used often early on in my career to keep compile times down, and as computers have got faster, it's now used to keep ABI stable. It doesn't seem to have gone away. So the idea here is you store an incomplete type inside your class, which defines the implementation of the class, and then that is sort of kept away in an associated CC source file. So over here we have a class which has got some members, and then it's got this implementation object inside it. And again, that won't compile yet as a direct member, because the impl class has not been defined yet. So the idea, what we want to do is define that class in the CC source file, but we can't then stick an instance of it inside A, because the compiler has no idea how much storage it's going to need. We also might want to support some sort of polymorphism. So we might require a member of our composite class to be one of a number of other types. So we might have a zoo with different sorts of animals in it. It'd be a boring zoo otherwise. A code checker could contain a bunch of different checking tools. A game can contain different sorts of game entity. Or a portfolio could contain different sorts of financial instrument. And our class is charged with the challenge of somehow reserving storage for this polymorphic data. So this is a thing of unknown type you want to store in your class. That sounds truly challenging. And then polymorphism I break down into two sorts. So we've got closed set polymorphism, where the thing which is going to go inside your class is of a type which will be decided at runtime, but it'll be taken from a list of available types. So inspired by Mexican food with my daughter, we have a taco which contains possible avocado, and then your choice of filling, and then sauce. No sauce is not an option. She didn't like that, but there it is. I don't make the rules. So storing a closed set polymorphic member is already possible through the standard library. So we've got things like variant and optional used here, so we can keep one of this list of things in our class, and that works by the compiler sort of knowing it needs to store enough memory for the biggest possible thing in your variant plus its alignment requirements. And then we have problems, and we have open set polymorphism, which is the case I've seen more often, unfortunately. So open set polymorphism allows users of a class to represent member data with types that weren't necessarily known about when the class was defined. So if you're writing software which is sort of a framework for other people to build things with. So I'm thinking like game engines or something. Like, you can't know about all the things people using your game engine are going to want to put in your game, otherwise you'd be writing the game. You're writing an engine, and they're going to plug things into it. So it's sort of, it's open-ended, it's user-extensible. So how do we store things of a yet-to-be-defined manner inside our class? A variant's clearly not an option, because we've no idea how big these things are going to be. So yeah, this is challenging, so some question marks. How are we going to do that? So, traditionally, we have supported polymorphism and incomplete types by storing a pointer as a member, and the pointer can be an incomplete type. So we can have our class A, which contains a pointer to a B and a pointer to another A. Alternatively, you could store the base class in a type hierarchy. So you have a base shape, and then your picture contains a single shape. And your shape could be a square, or could be a circle, or if you want to do a more interesting picture, you could have a vector of shapes, like go wild. So yeah, onto collections of pointers as members. We have an animal here, and we have a zoo with all the animals kept together in one big vector, and then we have a slightly safer instance of the zoo where the animals are divided up into different sections, like herbivores and carnivores. I think that would be better. And then the animals are all stored as pointers. But we got some issues with pointer members. So the compiler-generated special member functions will, as we discussed earlier, handle only the pointer and not the pointee. So they're all going to copy pointers. So if we copy the zoo, we're going to end up with two vectors all pointing to the same animals, and you're going to have to, I don't know, you're going to get into a mess, or you're going to have to write some code. You're going to have to write quite a lot of code, and it's going to be quite error-prone. And you're also going to have the issue with const not propagating to pointees. And again, if you're willing to write code and maintain it and never make any mistakes, then that's fine. But we can, I think, do a little bit better. So we want to model ownership in our composite. So we're going to have to do some work by manually maintaining these special member functions, or manually checking these const qualified member functions. So the manually maintain special member functions, I've seen that cause real problems in production code, and it's really embarrassing and painful, and something that one really feels could be avoided. And similarly with the const qualification, there's some code we once wrote to run some analysis on a client model, and we ran the analysis on the client model. I was like, it changes the behavior, but how can it do that? Well, we've got const in all the right places, but actually that wasn't enough, because you've got a few pointer members around the place, and suddenly all the guarantees disappear. So C++'s handling of pointers is not wrong, but in the examples above, we've really not accurately communicated what we want to the compiler, and the compiler's doing its job. It's right. And there are instances where pointer members are absolutely the right choice, but these things aren't really composites. So if you have a worker class, then it might have a pointer to its manager. So multiple workers would point to the same manager. It's not one manager per worker. When you create a new worker, you wouldn't expect the manager to be duplicated. You can scale all those up and down. So that looks like it's probably fine. Similarly, the worker here won't get, if the worker gets destroyed, then the manager won't get destroyed. So they need managing separately. So yeah, we can do better than pointers. Let's see what's available. So we've got smart pointers from the standard library. This looks good. Looks hopeful. So smart pointers have got different semantics to raw pointers, and they can be used to express a little bit more of our intent to the compiler. So we can use smart pointers to transfer ownership, express ownership, and free resources on destruction. So C++ 98 had stood auto pointer, and with the introduction of move semantics, we've improved somewhat upon that, and have some nicer smart pointers in C++ 11. Is anyone in the room just very curiously using auto pointer in their code base at all? I hope no hands go up. You are. Very good. In the past, but not now? No. Okay. Okay. Yeah. Auto pointer was a really ambitious piece of design. Like, it was really bold when the language features didn't quite support what they wanted to do, and yeah, it leads to curious bugs. I think it's gone from the world, and for the better. Thank you, auto pointer, for your work. So we have unique pointer, which is auto pointer done better with move semantics, really. And we can use a unique pointer to express our component relationship. So this is definitely an improvement over the raw pointer because it's going to write a destructor for us. Yay, that's good. No resource leakage. It's going to write move constructors for us. Also good. No resource leakage. No weird copies. But unique pointer is not copyable, so the compiler won't be able to generate a copy constructor. So we could write our own copy constructor, which might not be terrible. But the more worrying one to me is unique pointer is a pointer, so it doesn't do this const propagation, so the standard library. Smart pointers don't do const propagation because really the clue's in the name. They're smart pointers. They shouldn't do const propagation because pointers don't do const propagation. So we're going to have to check our implementations of all the const qualified member functions ourselves all the time, every time you make a code change to check they're doing the right thing. And I think we can do better. So what else do we have? We have shared pointer. Well, yeah, is this any better? I don't think so, really. So the compiler is now going to generate all the special member functions for us. We're going to get destruction, which is going to work properly. It's going to generate move, which is going to work okay. And it's going to generate copy. But the copy won't actually copy. It's just going to create another reference to the same object. So now we've introduced shared mutable state in our system. And whatever problems we had before, I think we probably now have one more. So yeah, let's not do this. I won't ask for a show of hands here. Yeah, we could do shared pointer to const t. Maybe this is a bit better. Keyword const coming up again. So the compiler is going to, again, generate all the special member functions for us, so that's good. Copy and assignment will add references to the same object. But it's a const object, so we don't care, because you can't modify the thing. So that's really good. So this looks like a pretty good candidate. Unfortunately, we can only call const qualified member functions now. So if you want to mutate stuff, let's look further. So we're proposing the addition of 2 new class templates to solve these design issues we've seen. We have polymorphic value, and we have indirect value. So with polymorphic value, it's another class template, so our class A would have a polymorphic value B member, and the compiler will now generate all the special member functions correctly, and polymorphic value by design will propagate const. It's a value rather than a pointer. So const qualified member functions can now actually be verified by the compiler. So B for polymorphic value is able to be a base class, and the object little b can then store an instance of any derived type. Copying and deletion will work correctly, and it'll copy the derived type as we want it to, as polymorphic value is implemented using type erasure. So what's this thing look like? So polymorphic value is a class template with a single template argument, which is the base class of the types we want to store. And we have some constructors. We have a default constructor, which will construct this thing in a sort of empty state, like a sort of unengaged optional. And then we've got a value constructor, emplacement constructor. I don't know what that name is. So optional's got something similar. We do one here. So we give it the type we want to construct, and then the arguments you want to construct it with, and then it will emplace it inside the polymorphic values ownership block. It says over here restrictions apply because the sphinai stuff is horrible to look at on the screen. Apologies if sphinai was in your slides earlier, anyone. So yeah, the thing you're constructing needs to be derived from the base class, or be an instance of the base class. And then there's another constructor, which we'll go into in a little bit more detail later on, which allows you to construct a polymorphic value from a pointer. A polymorphic value will then take ownership of that pointed to object. And you provide it with a copier and a deleter, and they'll deal with the copying and deletion. So this allows you sort of maximum possible level of customization. This constructor is dangerous. Like, this language provides you with some sharp knives, and this one is particularly horrible. So I would, if you do use this class, I would avoid this constructor unless you have some compelling reason to take hold of it. But sometimes you do, and this lets you get right under the hood and modify things. We have move and copy, which pretty much do what you'd like them to do. So the move and copy of polymorphic value of the same type will just create a copy of the same polymorphic value, and then you can create a polymorphic value from a further derived type. So yeah, and the same with moves. Assignment, you can assign directly to a polymorphic value of the same type. both move and copy style. And then we have modifiers and observers, and this is where sort of the magic happens, not in swap, but in the const overloads for operator star and operator arrow. And that's going to ensure the const propagation happens. So if you look at things like unique pointer and shared pointer, they don't do this. They've only got one operator arrow and operator star. Cool. And, you know, because shared pointer and unique pointer have got one, why not make a polymorphic value? I don't want to feel left out. So how do we implement this thing? So as I mentioned before, it uses type erasure inside. So our reference implementation, which this is now loosely based on, I think, contains a control block and then just a raw pointer to the object inside. We don't really want to be calling virtual dispatch for every single bit of pointer access we do, so caching that pointer, I think, is probably a useful optimization, but I'd be happy to talk to people offline about that. And the work is really done by the control block. So when we create a copy of the polymorphic value, then it will use the control block inside the polymorphic value we're copying from and call the clone function on that. So type erasure is, danger of sounding a little bit woolly. Type erasure sort of lets you treat a function as if it were virtual, using a little bit of sort of mechanics and just doing the virtual dispatch somewhere else. So really what we're doing internally in polymorphic value is making the copy constructor into a virtual function. Now, obviously, you can't do that because it's a language change, and I'm not advocating doing it, but you can use the trickery inside type erasure to give you all the mechanics of virtual dispatch on a non-virtual function. You can do this for other things. It doesn't need to be copy constructors. It's a cool trick if you've not seen it. The operator arrow, operator star, they're really straightforward to implement. Like you just return the pointer, and then the appropriate const qualifiers will be added. So let's dig into that control block because that's where the interesting stuff's going on. So control blocks all inherit from a base class. So yeah, the way to add virtual dispatch to something is to add virtual dispatch. So we start off with our base class. So it's got a virtual destructor, as you'd imagine. It's got, sadly, a virtual function to get hold of the pointer, which we aim to only ever call once. And it's got another virtual function to invoke the copy, this clone function. So we can support constructors which will take sort of a value form. So you give it the object you wanted to, the type of the object you wanted to create, and the arguments you want to create it with a special control block. So that control block, we call it a direct control block, and it inherits from control block. And in its constructor, it takes that set of template arguments and will then create an instance of the U object contained inside. And then in its clone function, it'll create a copy of that U, because that U needs to be copyable. And it'll create a new direct control block from that. So the control block knows how to copy and delete the object it knows, it owns, so we don't need to do any work. So this thing going in here, this class U, this thing does need to be copyable, otherwise this isn't going to work. Like polymorphic value is not going to make magic things happen. If you have some derived type which is non-copyable, then like we can't help you. Okay, and I've lost track of what I'm doing. Yes, I don't know what that slide's doing now, I'm sorry. So yeah, copying from another polymorphic value. So we can support constructors like of this form with another specialized control block. So notice that the polymorphic value we're constructing from is of a different type. So it's a U rather than a T. So this is handled with what I've called a delegating control block, which is a control block which wraps another control block and then just forwards things through to it. So that'll allow you to sort of move down type hierarchies. And you can see this being used inside the copy constructor, the sort of other copy constructor of polymorphic value. So it creates an instance of this polymorphic value of U, and then it will create this delegating control block and assign that to its control block. and then the nasty constructor. So we can support constructors which take this pointer, a copier, and a deleter, reluctantly, with another suitable control block. So our pointer control block has got a unique pointer to the object we're taking ownership of, and a deleter, because unique pointer allows you to specify a deleter for something. Unique pointer doesn't have a notion of a copier, so we have to keep the copier somewhere else. And yeah, it takes ownership of this pointer, so the unique pointers are constructed with the pointer you passed to the constructor moved in, and the deleter and copier are moved into the control block. And then the clone function will create another instance of this pointer control block by invoking the copier. We don't need to invoke the deleter ourselves because unique pointer is doing that machinery for us. You could rewrite this yourself with get rid of unique pointer and then just stick a U star and a D in there. It wouldn't make a big difference. And then this is used inside the constructor of polymorphic value by creating a control block, as we've seen in the patterns before. So this implementation here is not really too onerous or complicated. So there's an assertion in here, and I said there were sharp knives in this language, and then this is a particularly bad one. So this assertion is really quite nasty if this fires. And if you're building without type information on, then you're not going to have this sort of check for you at runtime. So yeah, care must be taken when using this. So the danger is that it'll slice. So if the dynamic type and static type going into this constructor aren't the same, it won't know, and it'll use the wrong type, and it'll do all our type erasure machinery using the incorrect type information, and then things will go wrong. So yeah, be careful. Or maybe don't use this constructor. So we put it in there because in code bases where people are trying to solve this problem by having a virtual clone method on their classes, one needs a migration path because it's just working really hard for weeks and weeks and then moving everything from having a virtual clone method to using polymorphic values doesn't seem like a very tenable migration path. It might be nice to have things compiling along the way. And you can make use of this constructor. You can specify a copier which will call the clone method on your class, so you can gradually migrate over and piece by piece start using polymorphic value everywhere. So it is a necessary migration tool, but maybe not one to keep around long term. So how would we use polymorphic value in our code? So our reference implementation of polymorphic value is a single header file. It's a header-only library, and you can include it in your C++ project by just grabbing the header from our reference implementation, which we've got MIT licensed. If anyone wants to use it and doesn't like the terms of the MIT license, then drop me a message and we can find another license to license it under. It would be really nice to see people using this and get some user feedback. Cool. Okay, so I promised 2 additions. So the second one is indirect value. So indirect value, very much like polymorphic value, is a class template. And again, we'll let the compiler generate special member functions correctly, and it will propagate const. So it's a value. It's not a value which is stored in your class, though. It's stored somewhere else, hence the name indirect value. So the B used in indirect value can be an incomplete type, but we now have a restriction that the object stored can only be an instance of B. So copying and deleting the object will work without virtual dispatch. So this indirect values class template now takes 3 template arguments. The type we want to store, which we saw in the previous slide, and in a little bit more detail. It also takes a copier and a deleter. Only the first argument is mandatory. In its absence, we'll use default copy, which we're proposing to add, and default delete, which already exists in the standard library and is used by unique pointer. And we have our constructors. So we have our default constructor, which will stick it into a sort of unengaged state, so it's got nothing in it. And just like polymorphic value, you can do this in-place construction. We don't need to specify the type going in there now. The type is implicit because you're not allowed to put derived types into it. And indirect value also has this nasty pointer constructor for much the same reasons polymorphic value did. We've got move and copy, which are now much simpler because we don't have to interact with any derived objects. We've got no class hierarchies to worry about. So move and copy and assign are all quite simple, straightforward. And we have our modifiers and observers, which should be identical to those from polymorphic value. Modulo some no excepts, which seem to have leaked in or leaked out. So we've got our operator bool, see if it's in its engaged state or not, and then we've got our const and non-const qualified operator arrow and operator star, which will give us the const propagation we want. So indirect value, because there's no ambiguity about the type, also specializes hash if the type inside specializes hash. And it will support three-way comparison if the type inside supports three-way comparison, and it'll support binary comparison if the type inside supports binary comparison. I'd like to be able to do this for polymorphic value. I think it's probably hard, and in general, I can't see a decent way of doing it without significant cost. But if anyone has any suggestions, I'd be interested. So how do we implement indirect value? So indirect value could be naively implemented with a raw pointer. So we have this T star pointer member, and then our copier and our deleter, and then we got our accessors, const and non-const overloads of operator arrow and operator star. So as we said, we don't need type erasure or virtual dispatch to create copies of an indirect value. Type of the owned object is known at compile time. If present, it needs to be a T. If the object's present, then the copy constructor of indirect value will just call its copy object on the dereference pointer to get a new object. And deleting is similarly simple. We know what's in there, so we'll just call the deleter on the pointer to destroy an owned object. So going back to our naive implementation. We want to avoid allocating storage for the copier and deleter where possible. If the objects have got no member data, then we don't really want the object to be any bigger than the raw pointer. Like it seems sad that the copier and deleter are taking up useful address space. So our reference implementation, with great thanks to Anthony, uses the empty base class optimization to eliminate the need for storage for empty copiers and deleters. A little bit of a snippet, so this is done by deriving from other classes, which can squirrel away all the need for storage. I think one could probably employ no unique address from C++20 to make this just work without having to do clever thinking, which is always good. But I haven't tried this out because I haven't got anything that supports no unique address. So how would you use indirect value in your code? So indirect value, again, is a single file, header-only library, and can be included in your C++ project by using the header from our reference implementation, which is linked over here. Again, indirect value is licensed under the MIT license. And if you want to use it in your code and that's problematic, let us know, and we'll see what we can do. So, yeah, values versus references. So the two class templates we've proposed adding are let you create value types, which treat the objects they own as values, so they're different to pointers. They delete the objects they own on destruction, and they'll copy the objects when they're copied. So value types are the right choice for design of composite classes. So we saw with vector and map, the copies and the const propagation all works, all does the right thing. Both indirect value and polymorphic value can be default constructed in an empty state. And this makes them into regular types. There was some significant design discussion about this. But this is the right choice because they need to interact with standard library types like map and vector, which expect to see regular types. So all the sad things about nullability don't go away with polymorphic value and indirect value. But hopefully they will be replacing pointers in people's code, so that's not introducing a new problem because nullability was already there. There are 2 papers in flight to add polymorphic value and indirect value to a future version of the C++ standard. And now that travel restrictions are lifted, we're hoping to resume our work on standardization. Yeah, so I'd like to give my thanks to Sean Perrin and the C++ Library Evolution Working Group for some very interesting early discussion, specifically in the design of polymorphic value. And also thanks to our GitHub contributors who've worked quite extensively recently to considerably improve our reference implementations. And that's a wrap. Thanks all.